Welcome. Today we are going through lesson 13.1, which is about right triangle trigonometry. So to start, we're going to talk about what trigonometric functions are. These are functions that relate an angle of a right triangle to the ratios, so looking at fractions of two side lengths. So we have a right triangle, you can see it in the picture below, and we use trig functions to relate the angle to the ratio of two sides that are near it. We use the Greek letter theta, which is that kind of oval with a line through it, to represent the measure of acute angles in the right triangle. So again, we kind of have an example here of what's going on. So we have a right triangle. You can see theta there in one of the acute angles. And theta can represent whatever angle we need it to of the acute angles, but everything's going to be based on that one that is represented by theta. So when we have theta in that corner, of course, the angle opposite of that right angle is called the hypotenuse. And then the other two are the two that we can kind of label based on where that theta is. So since theta is in that bottom left corner, that side that's across from it is called our opposite side. And the side that's next to it, that's not the hypotenuse, is called the adjacent side. So the two sides that make up that theta angle are the adjacent and the hypotenuse, and then the other third side is called the opposite side. So we take those sides and we put them into ratios based on that angle of theta. So here's what our trig functions look like. We have 6 of them. The 3 on the left are our basic trig functions. The 3 on the right are what we call our reciprocal functions. So you can see that labeled over there. For the 3 basic ones, we have sine, which we abbreviate with sin, but we still say it's sine, not sin. So the sine of theta is the relationship or the ratio between the opposite side divided by the hypotenuse side. So based on where theta is, the sine of that angle is the opposite side divided by the hypotenuse side. The cosine of theta, so we abbreviate that with cos, but we say it cosine, is the adjacent side divided by the hypotenuse side. And finally, our last basic one is the tangent, which we abbreviate with tan. And tangent is the ratio of opposite over adjacent. So those are our 3 basic trig functions. Then we have those 3 reciprocal functions, and we should know that reciprocal, of course, means the fraction is kind of flipped upside down. So cosecant is 1 over the sine function. So when we do that, what that does is it flips the ratio. So it becomes hypotenuse over the opposite side for cosecant. All right, the reciprocal function of cosine we call secant. So secant is 1 over the cosine of theta. And what that does is it flips that cosine ratio to hypotenuse over adjacent. And then lastly, we have the reciprocal of tangent. So that would be 1 over tangent theta. We call that cotangent. And again, that flips that reciprocal, or the original function, to the reciprocal, which makes it the adjacent divided by the opposite. Okay, let's use those 6 trig functions to find everything about this example triangle we have here. So in this example, we know that the 2 sides that are not the hypotenuse are 9 and 12. So to do our trig functions, we need to know the length of all 3 sides of the triangle. So we need to find that third side to start with. So to find the third side of a right triangle, I can do the Pythagorean theorem. So that would be a squared plus b squared equals c squared, c always being the hypotenuse, so that's what we're trying to find here. So when I simplify that out, I would get 81 plus 144 equals c squared. And when I add those together, I get 225 for c squared. And so I'm going to square root that to get the c alone. And I'm going to get that 15 is the value of c. So that means that this side length over here is 15. So now looking at where theta is, it helps me often to be able to kind of label the sides based on where theta is. So if theta is in that bottom right corner, the one across from it is my opposite. This is the hypotenuse. And then that means that this one next to theta is the adjacent side. So we can use those to help us fill in our ratios. So when we write our ratios, we just write them as fractions. So sine is opposite, which is 9, over hypotenuse, which is 15. Cosecant, remember, is the reciprocal function of that. So I can fill this in by flipping that sine ratio. All right, next up we have the cosine. Cosine is the adjacent side, which in our case is 12, over the hypotenuse, which is 15. And the reciprocal function of that secant would be 15 over 12. And lastly, we have tangent of theta. So tangent is the opposite, which is 9, over the adjacent, which is 12. And then the reciprocal of that would be 12 over 9. So those are the 6 trig functions for that particular triangle. Now, we have some special cases here. So we're going to look at the trig ratios for a few special angles. You've probably seen these angles before. They're 30, 60, 90 triangles, or we also have a 45, 45, 90 triangle. So those trig ratios for those particular angles are kind of unique. And so we are going to use them going forward in this trig unit. So we're going to identify them here. So we are going to start with the 30-degree angle. So we are basing everything off of this 30-degree angle in this top triangle. So we have all 3 sides labeled, so we're just going to go through them. So remember, sine is opposite. So in this case, this would be my opposite. This would be my adjacent. And this would be my hypotenuse. So for 30 degrees, opposite is 1 over hypotenuse, which is 2. So the sine for any 30-degree angle in a right triangle is 1/2. The cosine is adjacent over hypotenuse. And then the tangent is opposite over adjacent. And when we rationalize that, we know that it would come out to the square root of 3 over 3. So my inverse trig functions there would be 2 over 1, or just 2 for cosecant. Secant would be 2 over the square root of 3, but again, when we rationalize that, it comes out to 2 square roots of 3 over 3. And the cotangent would be just the square root of 3 over 1, or we can write it as the square root of 3. Now for this next column, we're going to base everything off 45-degree angle. And again, since it's a 45, 45, 90, the legs are the same, so it doesn't really matter which 45-degree angle. Any 45-degree angle in a triangle is going to have these 6 trig ratios. So let's call this one across from it the opposite, this one the adjacent, this one hypotenuse. So for this one, opposite is going to be 1 over hypotenuse, which is the square root of 2. Rationalizing that, I get the square root of 2 over 2. Now the cosine is going to be the same because it's still 1 over the square root of 2. So cosine and sine for 45-degree angles are going to be the same because their legs are the same. The tangent is opposite over adjacent. That's 1 over 1, so just 1. So for our reciprocals here, the reciprocal of 1 over the square root of 2 is the square root of 2. And just like sine and cosine are the same, cosecant and secant are going to be the same. And the inverse of, or reciprocal of tangent is cotangent, and that's still just 1, because 1 over 1 is still 1 over 1 in the reciprocal form. All right, lastly, let's base everything off the 60-degree angle. So when we switch to the 60-degree angle, now this square root of 3 is across from the 60, so this becomes my opposite. this becomes my adjacent, and my hypotenuse stays the same. So that hypotenuse never changes, but the opposite and adjacent can change depending on what angle we're looking at. So looking at sine, we have opposite, which is square root of 3 over the hypotenuse, which is 2. For cosine, we have the adjacent, which is 1 over the hypotenuse, which is 1/2. And then tangent is going to be opposite over adjacent. So that's square root of 3 over 1. So I'm just going to write it as square root of 3. All right, for my reciprocal functions, when I flip this one, or when I flip sine, we're going to get 2 over the square root of 3, but I have to rationalize that. So it comes out to be 2 square roots of 3 over 3. For secant, 1 over 2 reciprocal is 2 over 1. And the reciprocal of the square root of 3 is 1 over the square root of 3. So when I rationalize that, I get square root of 3 over 3. Now, those are some special ones that we can use to help us. And we can use any trig functions to help us solve for some missing values in triangles. So for this example, we have a 60-degree angle. And based on that, we are going to figure out what the trig ratio is we can use to solve. So these 3 steps kind of help us, and these, even if they're not written out on every question, you can definitely go through these in your head to help you figure it out. So for this one, based on this 60-degree angle here, x is opposite, and the 14 is across from the 90-degree angle, so that makes it the hypotenuse. So in this triangle, I am given the opposite side and the hypotenuse side. When I have opposite and hypotenuse, I know that that trig function that goes with opposite and hypotenuse is sine of theta. So I'm going to use those 2 pieces of information to help me set up an equation and solve for x. So we're going to say the sine, and I know theta in this case is 60, is the opposite side, which is x, over 14. So when I solve that, I know that the sine of 60 from my table up here, sine of 60 is square root of 3 over 2. So I can substitute that in and say the square root of 3 over 2 is x over 14. So we are substituting in what we know the sine of 60 is. That's why those special angles help us a lot. And now I can solve this proportion. So I would get the 14 square root of 3 equals 2x. I would divide both sides by 2 to get x alone. And then I would simplify. So 14 divided by 2, that's 7 square roots of 3 for what the value of x is. Okay, so now we are going to use that and take it a little bit further into solving triangles. So we use trig to help us find all kinds of pieces of information about different triangles, and we call that solving triangles. So when we ask you to solve a triangle, we are finding all the unknown side lengths. So you need to find the length of every single side, all 3 of them, and the angle measures of a triangle. So when you solve a triangle, you're gonna know all 3 angles and all 3 side lengths. To find the side lengths, we can use the Pythagorean theorem, or we can use trig ratios like we did in that last example. To find the angle measures, we can use complementary angles. So remember, 2 angles add up to 90, or we can use the inverse. Inverse trig functions help us to solve things. So if I want to get theta by itself, I want to solve for the angle, we use what's called the inverse, right? When we are trying to get rid of addition, we subtract because they're inverse operations. Or when we multiply, we have to use division to get rid of it because it's an inverse operation. Same thing here. If I want to get theta by itself and solve for it, I can use what's called the inverse function. So we write that as sine to the -1. That is the inverse sine. Same thing for cosine. To get theta alone, we do the inverse cosine. And for tangent, we do the inverse tangent to get theta alone. So that -1 power is what indicates that we're doing the inverse function to find the angle. So let's put that all together here for a couple of examples. In example 3 here, we are given one side length and then one or two angles. We have the 90-degree angle and then the 42. So when I am given two angles of a triangle, I can find that third one by using those complementary angles. So this right angle is obviously 90 degrees, so I know the other two have to add up to 90. So I can do 90 minus 42 to figure out what's remaining for that third one, and I would get 48 degrees. So I know this little angle down here is 48 degrees. Now I need to find the side length. So I have all three angle measures. It's good. Now I need to find all three side lengths. So I have one. I need to find some other ones. So this is one of those things where you can do this a lot of different ways. I like to base it on the information I'm given rather than just in case I found the angle wrong or something. I like to base it off the one I was given in the problem. So I'm going to base everything off my 42 here. So let's start with A. If I want to find A, from 42, A is across from it, so A is opposite, and that 12 is adjacent. Again, if you used the 48, that's fine. You just would label things differently based on that 48-degree angle. So, based on that 42-degree angle, I am trying to find the opposite, and I know the adjacent. So opposite and adjacent is tangent. So I'm going to set up the tangent of 42 is A, the opposite, over the adjacent. So into my calculator, we're going to need a calculator to do this. I would type 12 times tangent 42. You want to make sure that your calculator is in degree mode. So I'm going to type in 12 times the tangent of 42. You should have tangent, sine, and cosine buttons on your calculator to use. And again, make sure you're in degree mode. When I do that, I get that A is about, we're going to have to round a little bit, 10.8. So this side over here is 10.8. So we have all three angle measures figured out. We have two side lengths figured out. So let's find the third one. For C, I know that that's the hypotenuse, and I was given the adjacent. So again, I like to use the ones I was given. So adjacent and hypotenuse, that is cosine. So I'm going to set up the cosine of 42 is adjacent over hypotenuse, which is C for us. So we need to find that C value. So solving that, I'd multiply C times the cosine of 42, and that would leave me with 12 on the other side. And then to isolate C, I would divide by cosine 42. So into my calculator, I would type 12 divided by the cosine of 42. And when I do that, I get approximately 16.15. So this hypotenuse is 16.15 long. It always helps to check, make sure that hypotenuse is your longest side. Remember, it should always be the longest side. So that is a solved triangle. I've got all three angle measures, all three side lengths. Let's try one more example here. So in this one, I am given two side lengths. I need to find the third, and I only know the 90-degree angle, so I'm going to need to find two angles. So when I know two sides of a right triangle and I need to find the third, I'm going to do the Pythagorean theorem. So in this case, 10 is the hypotenuse, so I am going to do a squared plus 8 squared equals 10 squared. So when I solve that, I would get that A is the square root of 10 squared minus 8 squared. And that's going to give me the square root of 36, which I know is 6. So this side length over here is 6. All right, so I've got all three side lengths. Now I need to find the three angle measures. So I know one of them is 90, and I need to find another one. This is where we're going to use those inverse trig functions. So we can find either one first. It doesn't really matter. Let's start by finding the angle measure for A. So for A, the side I was given, the side length 8, is adjacent. And we already know the hypotenuse is down here at 10. So we're going to use that inverse trig function. So I'm going to set it up like normal. I'm going to say that the cosine of angle A is adjacent over hypotenuse. And then again, we're going to use that inverse trig function to solve for the angle. So I'm going to say A is the inverse cosine of 8 over 10. And if your calculator has sine, cosine, and tangent buttons, they should also have the inverse buttons there to help you out. So you're going to hit the inverse cosine of 8 over 10. And when I type that in, I get an angle measure that's about 36.87 degrees. So this angle down here is 36.87. And then the last thing I need to find is angle B over here. So for angle B, that 8, that side length that's now 8, is opposite of angle B. And then I'm going to use my hypotenuse again of 10. So opposite and hypotenuse, that's sine. So the sine of angle B is 8 over 10. So I'm going to do my inverse trig operation here and find the inverse sine of 8 over 10. And when I type that into my calculator, inverse sine of 8 over 10, I get about 53.13 degrees. So that is how we use trig to solve triangles. We'll see you next time.